Morning, everyone. Welcome to the seminar series. Today we have Joe On, a visitor from Hawaii University. He's a NASA Hubble Fellow there right now. Originally he comes from Singapore, where he did his bachelor studies and then moved to Yale University, I believe, for a master degree and PhD program. And obviously after that moved to the University of Hawaii, so he seems to like the United States very much. He specializes in theoretical astroseismology, I believe, with a focus on evolved stars, and today he's going to talk about mixed modes. So please, Joe.
Hi, this is Lloyd. Cool. Thanks for the honor of speaking to you. So as Andrew correctly says, I'll be talking to you about mostly evolved stars. And I know that there are experts on seismology in the audience, so I hope they will forgive me for spending some time providing some background and motivation for why we want to study these evolved stars in the first place. Okay, so I specialize in studying a particular kind of star known as a solar-like oscillator, right? And the reason why we study solar-like oscillators, or for that matter, study seismology in general, is because everything we know in astronomy is built on stellar astrophysics. And seismology is one of the very few ways, perhaps the only way, we have of looking directly at the inside of a star. And that's how we better understand stellar astrophysics, right? So solar-like oscillators occupy only a very narrow range of, a very narrow area of the kingdom of stars. So this is a Hertzsprung-Russell diagram showing in various patches different kinds of variable star. And solar-like oscillators only occupy, this part of the HR diagram, but that's still sufficient to generate a very rich set of phenomenology that I'll spend most of my time today discussing. So what is a solar-like oscillator? Well, if you look at the sun over a sufficiently fine temporal resolution, you will notice that it varies over time. The sun is a variable star. And this elicits some surprise every time I give an outreach talk, but it's true. If you look at the sun in photometry, this is what you'll see. You'll see that there are inhomogeneities on its surface. If you look at the sun in radial velocity, you will also see inhomogeneities in radial velocity superimposed on top of the rotational redshift and blue shift that arises from the rotation of the sun, right? And these inhomogeneities emerge from local velocity structure arising from, just random convection, right? And you might think that this is entirely stochastic, but if you were to average this over the visible disk of the sun, you would get variations in radial velocity that are coherent. And the reason for this is that these tiny stochastic variations in the fluid velocity field couple to global acoustic oscillations, sound waves, that may interfere with themselves constructively to yield normal modes of oscillation. So these are the pulsations that we're interested in. Okay? So if you were to integrate the radial velocities, these radial velocity structures over the entire visible disk and keep track of how they evolve in time, they will appear not to stay still, but to vary over time. If you were to look at these variations in the frequency domain by taking a Fourier power spectrum, you would see coherent peaks, right? So each peak in this Fourier power spectrum corresponds to a normal mode of oscillation. You see that these peaks form, more or less evenly spaced series of modes, right? So each evenly spaced series of peaks corresponds to a family of modes with the same horizontal shape, which we will get back to later. And the characteristic spacing between these overtones of modes in the same family we call delta nu, the large frequency separation. You can think about that as being proportional to, or depending on the sound travel time of the sun, in the same way that the spacing between overtones of a pipe or a flute also depends on its sound travel time. Okay, so the characteristic property of these solar-like oscillators is that you see lots of modes at any given time, right? And that's because of the stochastic nature of how these modes are given kinetic energy. They are pumped by random motions owing to convection, and because of this, basically every mode which can have kinetic energy close to some characteristic convective frequency will have kinetic energy. And this makes life pretty easy when we want to interpret peaks that we see in the power spectrum. Okay, so In principle, we could do similar analysis for stars other than the sun. We could measure the radial velocities over time, take power spectra and see, and look for either peaks in the power spectrum, or if we don't see peaks, at least look for an overdensity of power in the power spectrum. And this is a map of every star we did this for from 1995 to about 2008. That's not a very large number of stars, right? And that's because taking radial velocities is very expensive. You need to commandeer a telescope to stare at one star for days at a time with a cadence of maybe taking a picture of a star, maybe once every couple of minutes. So that's not economically feasible. And it turns out that most interesting stars are not that bright, so we can't even take radial velocities of them anyway. So the mitigating strategy that scientists have turned to over the last now decades is that rather than taking radial velocities, we take disk-integrated photometry. So we measure the variations in the brightness star and the brightness of a star and how it changes over time. Right? And you can do something similar. You can take the power spectrum of this brightness, and if you see peaks in the power spectrum of the photometry, then you can play the same game. You can say these are normal modes, and you can interpret the normal modes in the same way as you would those in the sun. Right? So we've been doing this for 2 decades now, since MOST. Most recently, we've been relying very heavily on Kepler and K2. And in the last, since I started my PhD, a lot of focus has been on TESS, which is the currently active photometry mission run by NASA. So far I've been talking about solar-like oscillators, right? And it might also perhaps not surprise you to learn that most solar-like oscillators are not sun-like stars, right? So the word solar-like refers to the kind of oscillations in these stars, rather than the kind of stars that the oscillations propagate in. So if I were to, show you the power spectra that we obtain from space for a number of stars of different surface gravities, whose positions on the HR diagram you can see here, you will see some trends as the surface gravity of the star decreases, right? So as the surface gravity of the star decreases, or equivalently as the star gets more evolved and hits up the Hayashi track as it goes off the main sequence, you can see that the characteristic frequency of these pulsations decreases, right? And because of this, we are able to use our measurements of this characteristic frequency and of the characteristic spacing between normal modes to make some inferences about the properties of the star. So these properties are known to scale with the global properties of the star, the mass, radius, temperature, and so forth, in that fashion. And we can invert these scaling relations to apply seismology as a tool for stellar characterization, right? So from these scaling relations for the global seismic properties, we can obtain estimates for, say, the mass and radius of a star. And this can be very widely and quickly applied to a very large number of stars at once, because it doesn't take a lot of effort to measure the large separation or the characteristic excitation frequency given the power spectrum. And you can use this basically to do all-sky mapping of masses of stars over the entire galaxy, for example. But with access to individual normal modes of oscillation, you can go further. Like I said earlier, you can use this to examine the interior structure of a star. And the capability to do this is more restricted in the sense that we only have good enough quality data to do this with a significantly smaller number of stars, at least on the main sequence. But the defining property of post-main sequence solar-like oscillators is that the mode frequencies look very different from those you would see in the sun or a similar main sequence star. So in order to better understand what I mean by this, I'm going to have to rearrange this power spectrum into a form that makes it easier to reason about the structure of these normal modes. Right, so I'm going to phase-fold them in the following fashion. I'm going to break the power spectrum down into chunks equally spaced by the characteristic overtone spacing. I will vertically stack the chunks, so this is phase-folding, right, in increasing order of frequency. And when stacked in this fashion, the power spectrum appears to have some kind of three-dimensional structure, which we will look at from above. Right? So this three-dimensional structure is in the form of several ridges of power. Right? You have vertical lines. And if the overtone spacing of the modes were completely constant, you would see exactly vertical lines, right? But they're not. You see deviations from verticality, and that tells you things about the inside structure of the star. So each of these ridges corresponds to a different angular degree, L. That is to say, a different horizontal shape of the modes, right? So this blue guy here corresponds to L equals 0. These are pulsating in breathing modes. They are spherically symmetric. The orange ridge over there corresponds to dipole modes. This gray one corresponds to L equals 2 quadrupole modes, and so forth, right? So in the main sequence star, the nice thing about solar-like oscillators, and what allows us to do inference so easily, is that when put on an Echelle diagram, the modes look very clean. They form vertical ridges. So I'll show you what happens when you go off the main sequence. As we evolve a star off the main sequence and across the Hertzsprung gap, you can see additional modes coming into the picture, interacting with the more or less vertical ridges, and doing complicated things that are very difficult to describe in words. But you can see on animation that something is happening and that's complicated, right? So what's happening here is that in these post-main sequence stars, there are two kinds of waves. So in the main sequence stars that I just discussed, there are pressure waves, which are excited in the envelope, and which propagate isotropically given a disturbance to the stellar structure. In these post-main sequence stars, we also have gravity waves, or buoyancy waves, where the dispersion relation, which I'll come back to in a minute, is different. What that means is that they respond differently to perturbations to the stellar structure. So these are the same kinds of waves you would see, perhaps, on the surface of a pond, where if you punch the pond downwards, the waves don't radiate downwards, they radiate horizontally outwards from where you punched it, right? So the physical properties of these waves are different, and because of that, the frequency eigenvalues are also different. So what happens over the course of stellar evolution, this is what makes the evolution on the earlier plot so complicated, is that over the course of stellar evolution, the P modes, which are shown at large amplitude here, decrease in frequency, and the G modes increase in frequency like so, right? Additionally, the P and G modes don't propagate independently, they talk to each other in the fashion that I'll describe more quantitatively soon. Right, so this coupling between the P and G mode cavities means that over the course of stellar evolution, a G mode and a P mode which come into resonance will exchange places, right? So this G mode becomes a P mode as a star evolves, and vice versa. This formerly P mode becomes a G mode as a star evolves. So if I were to unwrap this animation to put time on the horizontal axis, what happens is that on this diagram, if we were to make the P modes move on horizontal lines, the G modes increase in frequency, but the actual normal modes, the ones we actually see, evolve on these blue curves. They kind of interweave between the two families of possible modes, right? And they avoid the intersections of the two families of curves. And this is why we call them avoided crossings. So these avoided crossings are the reason why mixed modes are tremendously tough, or legendarily tough to work with. And they are the focus of my talk today, more or less. Okay, so where do these avoided crossings come from, and why do they make life so difficult? In order to understand this, I'm going to have to walk you through some physics, which I apologize for, but you guys probably like physics anyway, so. Okay, so in your undergrad physics courses, you might have seen something like this. This is called a wave equation, right? And it relates the temporal evolution of a wave to its spatial structure, right? So in a simple medium, which is homogeneous, isotropic, you can pretend that the speed of sound is constant everywhere and doesn't depend on position or time, right? And in that case, the wave equation looks like this. So since everything here is constant, more or less, except for the wave itself, which is the function f, we can take Fourier transforms on both sides of the equation, and we realize that you can just divide out the Fourier transform of the wave itself. And this gives us a relationship between the frequency of a wave and its wave number, which is basically 1 over the wavelength of the wave, right? And this is basically, if you've written an equation of the form, v is equals to f frequency times wavelength, that's it, right? And this is a very good description of waves, like sound waves, like the kind I'm making and which you're hearing. if you have a more complicated kind of medium, right, then you could, in addition to the sound speed, also have an additional constraint that, for example, the refractive index of the medium may be changing as a function of position, right? So we can encode that behavior in terms of what we call an acoustic cutoff frequency, which is position dependent because the wave has to turn around somewhere, right? And in that case, we can't directly take the spatial Fourier transform of the wave, although we can still do it in time. But what we can do is we can pretend that we have some function of position that in the limit of the wavelength being infinitely small acts like 1 over the wavelength, right? We call this a propagation discriminant. And the way we interpret this discriminant is that the wave is allowed to propagate like normal, where it is greater than 0, and it decays exponentially where it is less than 0, right? So for illustration, I've shown a scenario where the acoustic cutoff frequency is shown with a solid line. In this blue shaded region, the wave is allowed to propagate, and in the unshaded region, it is not allowed to propagate, right? So the wave behaves like that. You have, oscillatory behavior in the permitted region, and exponential behavior in the forbidden region. Okay, so the dispersion relation in an actual star is more complicated than that. So there's 2 kinds of oscillatory regions, and everything else is forbidden, right? So in particular, in a red giant, whose interior structure I'm showing, the 2 different propagation regions exist, are those near the surface, shown in orange, where P modes are allowed to propagate, and those in the interior, shown in blue, where G modes are allowed to propagate, right? So this is the kind of brute force numerical approach that, or quasi-analytical approach that we've been applying so far. And it's helpful in terms of classifying where the waves are exhibiting what kind of behavior, but it's less helpful in terms of actually doing calculations, which we've still been using brute force methods for. So I'm going to walk you through an alternative formulation with perhaps a different way of conceptualizing the separation between the G-like behavior and the P-like behavior of these modes. If you've taken a chemistry class, this might seem somewhat familiar, right? So I'm going to walk you through first a construction that's commonly used in physical chemistry called the method of molecular orbitals. And the method goes like this. Let's say that you fully understand the eigensystem of a particular atom, say the hydrogen atom, right? And now you want to make a molecule out of 2 hydrogen atoms. Now, if the 2 atoms were at infinite separation, then the eigenstates of the combined system are just 2 copies of the hydrogen atom, right? That's pretty easy. But if you were to bring the 2 atoms together to form a molecule, what you can do is you can treat the Hamiltonian of the combined system as, for example, the Hamiltonian of atom number 1 plus a small perturbation from atom number 2, or vice versa, right? And as you do this, what happens to the eigenstates as you reduce the interatomic separation is that they become combinations of the atomic orbitals of both atoms, right? So the ground state will be the ground states of both atoms interfering constructively. The first excited state will be the ground state of both atoms interfering constructively, right? And the difference in energy between the 2 can be written as some overlap integral between the 2 ground state wave functions of the 2 atoms, right? So there is an avoided crossing hidden here as well, in the sense that if, rather than considering a diatomic hydrogen atom, you consider a diatomic hydrogen-like atom, in the sense that you permit the charges of the 2 atoms to differ. In that case, the ground and first excited states of the molecular system exhibit an avoided crossing in terms of the charge ratio of the 2 atoms, right? And you can see that qualitatively, when they are far from resonance, they behave, they are very similar to the ground states of the atoms considered separately, and when they are close to resonance, then they are very strongly mixed, right? When they are far from resonance as well, you can also see that the difference in the energy eigenvalues appears to be a root of some polynomial, in this case of degree 2. So this is very suggestive of being the eigenvalues of some matrix, and actually that is exactly the case. In the limit, of many atomic orbitals interacting with each other to form molecular orbitals, what you would do is that you would express each molecular orbital as a linear combination of atomic orbitals, with the coefficients of this linear combination being given by the eigenvectors of some overlap matrix, and with the eigenvalues specifying the energy levels of each molecular orbital. So the situation in seismology is actually, surprisingly, entirely analogous, right? You have waves, normal modes, generated by some wave equation, which can be expressed in operator form, and you can express the operator generating these mixed modes as perhaps a G-mode wave operator with a small perturbation from the P-mode cavity, or conversely, as a P-mode wave operator with a small perturbation from the G-mode cavity. And if you want to express your mixed modes as some linear combination of pure P and G modes, then you just use exactly the same matrix machinery, right? You compute the same kinds of overlap integral of the full wave operator with respect to the pure P and G modes. You put them in this big matrix, you solve for the eigenvalues, and you've gotten your mixed modes, and you get your mixed mode eigenvalues with the eigenvectors telling you what the combinations of P and G modes ought to be for each mixed mode. Okay, so with this technology in hand, we are now able to better interpret the P and G components of a set of mixed modes presented to us observationally, right? So for example, one thing you can do is, given a set of G modes, you can put them similarly on a shell diagram, and by doing some clever coordinate transformation, you can get the mixed modes to give you what the pure G modes ought to be. And you can interpret these pure G modes in terms of rotation, I'm going to skip this plot, or in terms of magnetic fields, which some members of the audience have been instrumental in discovering. And I'm going to point out some student work also to do with interpreting these magnetic fields. So Nicholas Roy has been working on nonlinear perturbation theory for interpreting strong magnetic fields in combination with rotation in G-mode pulsators. And Emily Hatt, who is at the University of Birmingham, has been working on cataloging extensively the strengths of magnetic fields in many, many red giants all at once using automated techniques. But I'm not here to talk to you about G-modes today. I'm going to talk to you about the P-mode components of these mixed modes, which has so far largely been neglected. So returning to our observational diagram, we have, for a main sequence solar-like oscillator, a set of vertical ridges on its shell diagram, right? And we can think about not just the large frequency separation, which is the overtone spacing required to obtain this diagram by phase folding, but also the separation between different ridges on this diagram. So of particular historical interest to the people studying sun-like stars has been what's called the small frequency separation, which is the separation between this ridge and this ridge, right? So that's the separation between the radial modes, L equals 0, and the quadruple modes, L equals 2. So that's labeled on this diagram as delta nu 0, 2. All right. So the reason why this has historically been interesting is because if you do some math, you will eventually find that for a main sequence sun-like star, this quantity depends basically only on the interior structure of the star. So it doesn't depend on the near surface layers of the star. Additionally, its precise dependence on the interior structure of the star is on the sound speed gradient near the center of the star. So this expression is saying that the small frequency separation is a weighted average of the sound speed gradient of the star, with weighting increasingly heavy towards the center of the star. Now, as a star evolves on the main sequence, the chemical composition of the near center changes over time, right? And this causes the chemical composition, and therefore the sound speed, to change in a position-dependent fashion over the course of its main sequence burning. And as such, the small separation can therefore be used to accurately measure stellar ages for main sequence stars. And so for this reason, it has been used as a direct astroseismic probe of the stellar age. So let me show you what I mean. If you were to plot the small separation on the vertical axis against the large separation on the horizontal axis for a set of computational models of stellar structure, what you obtain is for a star of a constant mass, the star evolves along these. A star will evolve along colored curves like these, right? If you were to plot lines of constant age on this diagram, these are isochrones. These will follow these. The isochrones follow these dashed lines intersecting the evolutionary tracks, right? So so I've been talking mostly about the small separation, delta nu 02. But if you were to divide the small separation by the large separation, you get what's called the separation ratio. So that's R02 in some of my slides. If you were able to measure R02 and the large separation and put it on this diagram, you will see that basically by placing a point on this diagram, you will be able to just read off a stellar age from this diagram, right? So that's why people have been so interested in, making measurements of the small separation or the separation ratio for main sequence stars. But you might have already noticed something strange about these diagrams, which is this messy grassiness here. So any guesses as to why that is? So there is a clue in one of the animations I showed earlier, which I'll show again. Okay? So again, I show this animation, and I want you to pay attention to the small separation as the star evolves off the main sequence. So think about this from perhaps a computational perspective. How would you compute a small separation given this rapid evolution? Right, you won't. So what happens is that if you were to compute the full set of mixed modes here and attempt to measure a small separation from these mixed modes, you will get a lot of numerical noise simply from the avoided crossings happening as the G and P modes come into and off resonance. But that's a problem that we've just solved. We are now able to compute P or P modes from stellar structure, and as such, we are able to compute the smooth evolution of the small separation, or equivalently separation ratio, for sub and red giant stellar models. And so if you were to do that calculation, this is what you would get. It's a smooth curve, right, over the course of stellar evolution. The star evolves from 0H main sequence here on the right, and as the star goes off the main sequence and up the red giant branch, it heads to the left, and the small separation decreases over time, like so. So that's a first. But what happens if you were to compute that integral estimator we saw earlier, the integral of the sound speed gradient as a function over the stellar radius? If you were to compute that estimator for the small separation, this is what you get, right? So the small separation is supposed to be strictly less than the large separation, so something has clearly gone wrong here. And correspondingly, this means that we cannot interpret the small separations that we observe in the field as being related to this integral in any fashion. Okay, so what's gone wrong? To understand what happened, we first have to attempt to understand where this expression came from. So I will try to do this without going into the weeds too much. What I will do is I will describe the normal modes in terms of their radial displacement. So over the course of one oscillation cycle, at each point in the star, the fluid is displaced in the radial direction by a little bit in a periodic fashion, right? I will describe this as a function not of the physical radial coordinate, but in terms of the acoustic radial coordinate, the sound travel time from the center. And I will scale the eigenfunctions in a clever way so as to make the pulsations look more or less sinusoidal as a function of the acoustic radial coordinate. Okay, so what happens is that when you perform this coordinate transformation and this scaling, you can approximate the normal modes as being more or less sinusoidal up to an overall phase offset, right? So for radial modes, for example, we need some phase offset that I've shown in this slider. And let's say for L equals 2, we might need a different phase offset in order to get agreement with the actual normal modes we compute numerically. So it turns out that the small separation, or more accurately, the small separation ratio, can be expressed compactly as the difference between the phase offsets for the quadruple modes versus for the radial modes. Okay, so what went wrong is that when we derive the relation between the small separation and the internal structure of the star, we are actually making some small angular approximation in the sense that the integral expression we have tells us not the phase offset per se, but rather the tangent of the phase offset, right? And when we relate the small separation to the sound speed gradient, we are in effect making a small angular approximation. So let's see how valid this approximation is. I am plotting on these figures the quantity theta entering into our expression for the small separation, for the inner phase offset, right? And this I am showing for a main sequence star. So in order for the small angular approximation to work, we need these curves to go below 1 at some point in the stellar structure. And this assumption is well satisfied for the main sequence model shown here. For a red giant, however, this quantity never goes below 10-ish, right? And as a consequence of this, the small angular approximation that we are requiring for our integral estimate for the small separation breaks horribly for subgiants and red giants. And the remediation for this is fairly simple. We just don't make a small angular approximation and compute the full arctangent or whatever. And we get now a slightly more complicated expression for the small separation ratio. So in the limit, as these quantities go to 0, we recover the existing expression that we have in hand for the small separation ratio. But in the opposite limit, which is what we encounter in red giants, it turns out that the small separation doesn't actually depend on the internal structure, or at least shouldn't depend on the internal structure of the star. It goes instead as some ratio of the large separation and the characteristic excitation frequency. And that's a bit hard to believe, right? So let's do some numerical tests. So here I have plotted the small separation ratio of a series of stellar models, the same ones that I've shown in the earlier figure, where I showed the small separation itself. And here I show the values of our modified estimator with the limiting values in the limit of it not depending on stellar structure, shown with a dashed line. So there is an offset between the values returned by our approximation and the values that we compute numerically from the stellar structure. So there, aside from the constant offset between the two, which we can explain with higher order effects, there's also a bump here that we cannot explain with higher order effects, right? And we might wonder whether this might be interesting in terms of our ability to peer into the inside structure of the star. So, recalling what I said earlier about the small separation ratio depending on the difference between the radial mode and the quadruple mode interface offset, we can decompose the difference between the two into contributions from the radial modes and from the quadruple modes. And where we see the bump in the separation ratio, we see a bump in the radial modes phase offset, but not in the quadruple mode phase offset. And that indicates that if that bump depends on any property of the stellar structure, that feature in the stellar structure has to lie quite deep into the star, right? And one feature that does lie quite deep in the star, in these rather evolved stars, is the boundary of the convection zone. So here I show basically how the position of the boundary of the convection zone evolves over time, right? And as it does so, I also show on the right panel where we are on the Christensen-Dalsgaard diagram, on the figure with the separation ratio on the vertical axis and the large separation on the horizontal axis. And what we can see is that on this side, I'm showing basically the amplitude of the wave function at frequencies close to nu max. And what we can see is that where the bump happens on the right panel corresponds to where the convective boundary passes over the innermost maximum of the wave function close to nu max. And we can interpret this as we can unwrap the animation like so, right? The colors of this figure represent where the waves have highest amplitude, right? And where the waves have highest amplitude coincides with where the convective boundary of these evolved stars is, at frequencies that always coincide also with where we are seeing the bump in the small separation ratio. So we can conclude from this that if we see the bump in the small separation ratio, that means that the convective envelope currently is sitting at the innermost maximum of the P modes that we have access to in the star. So that's it. That's the interpretation. And this is a lot of theory work, but I'm quite excited to also announce that this has recently been observationally verified. So Claudia Reyes, who is a finishing PhD student at the University of New South Wales, did an ensemble of measurements of the small separations for red giants in the open cluster M67. She put them on this diagram. She calculated a stellar evolutionary track with a certain amount of overshoot, and the small separation measurements line up exactly on the track. And that pins down basically the behavior of the convective boundary as a function of time. Now, precisely what behavior do I mean? All of this discussion concerns the position of the convective boundary and how it moves in as a star evolves, right? But in a real star, the position of the convective boundary is not quite the same as we would expect in our approximations for stars satisfying spherical geometry. And that's because convection is a highly non-one-dimensional process, right? In general, convection happens in 3D, and as such, defining the position of the convective boundary is always a bit difficult. In particular, because convective plumes have some velocity, they can always overshoot the boundary of where convection is stable versus where it is not. So, phenomenologically, what we would see in a 3D hydrodynamical simulation like this one is that you have mixing of the star extending beyond the region of convective stability. This is called convective overshooting, right? And it is the position of this mixing, rather than the position of where convective flows are stable, that actually defines where the convection zone ends as seen by seismology. So to put things differently, our ability to probe the position of the convective boundary using seismology effectively permits us to constrain how much convective overshooting is happening in these red giants, right? So if you were to examine how the small separation ratio, or equivalently the differences between the interface offsets, depends on the amount of convective overshooting, which is shown by different colors, you see that there is some sensitivity. I unfortunately didn't put observational error bars on this, but the separation between the curves is comparable to or larger than the observational uncertainties that you would get. Right, so this is the basis of our next search for convective overshoot, which we just got funding for from NASA. Okay, so to wrap up, red giants exhibit mixed modes, which behave like G modes on the inside of the star and behave like P modes on the outside of the star. These mixed modes may be described as acoustic molecular orbitals in a publication that I wrote a couple of years ago. Using this separation between the P and the G modes, we can extract information from the P modes, and we can remediate a broken small angle approximation in our existing theory of P modes. This remediation of the small angle approximation leads to new theoretical predictions for how the small separation ratio depends on convective overshooting, which has recently been observationally validated. So yeah, that's it. Right. I've talked about understanding mixed modes as an object of interest per se. That's the fun part. And I've talked about using this new understanding to constrain the physics of convective overshooting. That's the profit. So that's my talk. Thanks for your attention.
Thanks, Joe, for an interesting and very clear talk. Time for questions. We have about 15 minutes. Don't be shy.
Thank you for the nice talk. I'm one of the non astroseismologist, so I'm more interested in the mixing stuff because I'm doing evolution. So you have shown this overshooting parameters. How is overshooting in these models you have shown implemented? Is it step or exponential overshooting? And
yes.
how
So
can I
these are
interpret
models generated with exponential overshooting, right? So are you familiar with MESA? Yes. So the parameter f over here is the FOV parameter for MESA's implementation of exponential overshooting. Yeah. I will also say that in our observational paper, we compared the observational values of the small separation ratio against evolutionary tracks generated with no overshooting and with twice the prescribed amount of overshooting. Right? And you can see a difference here. And the lever arm is provided by this particular feature in the small separation diagram.
Thanks.
More questions?
Hi, yeah, and thanks for the fantastic talk. I was just wondering, so in terms of the quality of data needed to do this kind of analysis, like you've shown an example here, was this like an unusually high quality data set for this star, or are there many stars that have this good data that you could compare with?
Which star do you mean?
Say this one, the one you've got on the
So
slide.
this is an open cluster, which means that we have light curves for several stars. Yeah. I think the data here is not of unusually good or bad quality. This is more or less standard short cadence K2 data. So there are more instrumental systematics than the nominal Kepler mission, but it's also not as nice as the nominal Kepler mission. But it's also not as bad as, for example, the instrumental systematics that we associate with TESS, where you have like large separations between individual windows. So I think the important thing that we require for analysis of this kind is data sets of unbroken length, which is difficult, but not that difficult to come by.
Okay,
Yep.
Thanks.
More questions?
In the diagram where you showed the evolution of the separation ratios, somewhere in your like 50 something on the slides, where you had the tracks exactly like one of these.
Okay.
I was noting that the sun is not on the one solar mass track. Can you
Yeah.
comment on this? I know it's not
So-
your work, but
Yeah, I didn't make this. So one issue with putting things on this diagram is that the position of things in the horizontal direction depends on systematic errors that we make in modeling the stars. Right? This is called the surface term, or near surface effects. And this can affect the value of the large separation we compute from a star, from a stellar model, with exactly the same stellar structure as something we see in the field. So for example, if you were to compute the large separation for a solar model, you would get something like 140 microhertz, even if its internal structure is exactly identical to that of the sun. But the sun gives us a large separation of 135 microhertz, and so it's the horizontal position that changes. But for the small separation ratio diagram, you can see that the horizontal position doesn't really change the estimate of the H you have, and so that's not that big a deal.
Thanks for the great talk. I was wondering, when you showed the result for the cluster, each point was an individual star. But I was thinking, like, if you have multiple modes in a star, they will slightly, well, where they probe will differ slightly. So could you learn something about where how the overshooting region looks just by looking at all the different individual separations?
In principle, you could. We didn't do that for the observational work because the data were not of sufficiently high quality for us to do individual mode fitting. So what we did for Claudia's paper is a bit different. I don't have a slide for this, unfortunately, but you can kind of visualize how it works from the shell diagram, I think. So the technique Claudia used is called the collapsed shell technique, where you first begin with a candidate large separation, which gives you an shell diagram like this, but it looks very noisy because the data is not that high quality. then you project in the vertical direction, and you just see, you know, 2 peaks here and 1 peak there, right? And the separation between the 2 peaks here can then be used as an estimate for the small separation. But you are correct. If you were able to do individual frequency measurements, then you would be able to get still more detailed information about the convective overshooting.
Thanks for the very nice class, Joel. Replacing my whole course this semester. Thanks a lot. You did it in less than 1 hour. Following on Vincent's question, can you actually do an inversion for the, I mean, core overshoot is really just a term to replace a whole bunch of opportunities that may occur and may intervene between rotation, magnetism, and waves even?
Well,
you try?
You could do in principle, if you had high quality enough data, you could do an inversion for the position of the convective envelope boundary. The reason why we haven't done it is kind of described in this figure. So I show with the blue points the entire Kepler sample of oscillating stars, right? And the region of interest where we have sensitivity to the convective envelope boundary, that's shown in gray. You will note that it kind of lies mostly in the gap between the long and short cadence of Kepler. So this is why we haven't been able to do it with Kepler data, because we just happen not to have any stars lying here as a result of the observational window function. But in principle, TESS is going to soon have 4 years of data, so perhaps we might find a star lying here in TESS. We've identified some already, shown in orange, and so those will be our first targets to look at.
There's time for more questions.
Hi, Joel. Thanks for this nice talk. I was wondering, so you showed for your cluster as well, but you only have one small frequency separation, but I guess you could use, is it possible to use both of them? Like you have 2 for the P modes, right? For the L equal to 0, 1, 2, and 3.
Yes.
So if you go back to your HL diagram, you actually, I guess maybe the difficulty is that you don't really see the other ridge, like the gray one, the dark gray one here sometimes.
Yeah, the L equals 3 small separation is really hard to pull out. Because this is just from geometrical effects, right? Because as you integrate over the whole disk, then the visibility of higher and higher degrees just gets washed out by geometrical integration. So as far as I'm aware, we have L equals 3 mode measurements for some stars from Kepler, but this is very hard for photometry. So if we wanted to get L equals 3 modes, in principle, we should be trying using ground-based radial velocities, because the projection effects just work in our favor there. But ground-based radial velocities are expensive and really impractical for getting a year-long baseline of the kind you would need for inversions.
Okay, cool. I was wondering, like, what can you do extra if you have this available then? So what can you do extra if you have the L equals 3?
Yeah, if you have the L equals 3 modes, in principle you get more resolution in the radial direction for structure inversions, because different families of L have different inner turning points, right? So for example, if all you had were just the overall phase of the modes, you could still do a very coarse kind of inversions by taking the difference between the L equals 1 and L equals 2 inner turning points, and that's one resolution element, right? So with L equals 3 modes, very roughly speaking, you get one more resolution element further out from the center.
Okay, thanks.
Still have some time.
Okay, more questions about mixing. So you have shown that you nicely can determine like the extent of overshooting, and I wondered how sensitive are your results to other mixing parameters. For example, if you use mixing as for MLT, standard MLT, if you change your alpha MLT value, like your mixing length, it would change like the structure of your star, and also should impact like your derived overshooting.
That is true. So ultimately, this will impact the interpretation of our results in terms of overshooting, right? So at the core, what we are truly sensitive to is the position of the convective boundary. So in principle, one could eliminate dependencies on choice of alpha MLT by doing something like an entropy calibrated mixing length. And no, there are alternative formulations that extend or do away with mixed length theory altogether. The important thing, however, is that having an observational handle on where the convective boundary is permits us to validate these theories in general, not necessarily in the form of overshoot. Thanks.
Plato will allow you to do that. Launch is December 2026.
Yeah, thanks. So it was a very clear talk for me. So thank you for dive into this field. So my question is regarding radial velocities. So for the solar stars, I think you showed a sub-meter per second diagram in the beginning introduction. For, let's say, F stars, or do you expect larger larger signals in the radial velocity space? And what is the maximum you would in terms of precision go for to characterize F stars?
Okay, so that's two questions.
Yes.
So
yes,
the first question is what kind of radial velocity precision we would expect. Yeah. What kind of radial velocity amplitude we would expect for an F star, right? And that's of order like 0.5 meter per second. The second question was whether we could use it to characterize F stars. The answer is we thought so, but the answer is probably not. And the reason for this is not what you might think. So in these power spectra, you will see that the individual modes are really well resolved, right? So you can see narrow peaks in the power spectrum. In an F star, the lifetimes of the modes are really short. So they stay coherent for a really short amount of time. And what that means is that the modes are really fat in the power spectrum, right? So if you were to make a similar Echelle diagram for an F star, the modes are so fat that you can't tell the L equals 0 and 2 modes apart, right? And so that limits the amount of structural information you can get from an F star, which is why we've generally not so far been too interested in seismology of F stars.
Okay, thank you.
There's still some time, not much, but maybe for 1-2 questions. In the meantime, Joe, maybe if you could go back to forward to slide 77. So what I've noticed there on the right-hand side plot,
yes,
is that there is some noise, and that noise seems to be increasing as the overshoot parameter decreases, which is suggestive of some numerical issues in the models.
Yes.
So what's wrong with our numerics, and if there is something fundamentally wrong, how can we actually use these models as a tool?
Okay, so this is a specific issue with the version of MESA I used to make these diagrams. So this ultimately is to do with how we define the position of the convective boundary, right? So when there is no overshooting, you would define the position of the convective boundary as basically where the Schwarzschild criterion changes sign, right? The problem is that by default, MESA doesn't remesh the neighborhood of the convective boundary more finely in order to be more accurate to give you this estimate. So because of this, if you were to keep track of the position of the classical boundary as it evolves, there's going to be some numerical jitter, right? And as a consequence of this numerical jitter, you also get jitter in the mode frequencies. So this is actually fixable. It's just I didn't fix it for this figure. Sorry about that.
So it's a resolution effect that you can solve with like adaptive meshing or something. Okay.
So there used to be, and there now is again, it's a long story, an option in MESA called convective boundary weight, right? And that tells you how many more mesh points you need to add to the model near the convective boundary in order to smoothly resolve it. So this was removed in version 1.2.7.7.8 and only very recently added back again. Yeah.
Okay, thanks. All right, maybe one more very last question if you want to. No? Then let's thank Joe again for his wonderful talk.
Thank you for having me.
So I believe Joe is still around today, so don't hesitate to approach him and talk if you want to, need to. Yeah, and tomorrow as well. Thanks.